Hello everyone, I'm Yueting from Tsinghua University. Today I'm glad to introduce our work, Selecting Real-World Objects via User Perspective Phone Occlusion. Mobile computing allows us to quickly and easily connect and interact with many nearby ubiquitously distributed appliances or get information from nearby objects. Using the camera to perceive the physical world is an intuitive way to enable the phone to interact with inside objects. For example, scanning the QR code, issuing the user-defined command, displaying a control interface, or performing multimodal interaction with voice and gestures. One of the key issues is how to make the smartphone quickly and accurately identify the target the user wants to interact with. Traditional method of two types of solution. The first is to actively turn on the camera and render the camera preview on the screen. The user confirms the on-screen target by tapping it or pointing an on-screen selector at it. These methods usually require multiple steps, such as opening the camera preview, waiting for the screen to render the camera preview, align the camera preview to the target, confirming the target, and finally speaking voice commands or interact with gestures. If we do not use the camera preview, we can use gestures to trigger snapshots, use the head gaze, or point directly at the target according to the user's proprioception. To improve the efficiency and accuracy of spatial interactions with smartphones without opening the camera preview and reduce user insecurity due to the lack of visual feedback, we propose to use a novel selection tools to simultaneously improve the efficiency, accuracy, and the user experience of interacting with inside objects using smartphones. That is, a resizable and rotatable rectangular region of interest, provided by the user's perspective phone occlusion. When the users want to interact with the objects inside, they raise the phone, block the target from their perspective, and trigger the gesture commands or speak directly to the voice assistant. In this paper, we mainly study the following three questions. Question 1. How do users mentally map the occluded area to a specific target? Question 2. Based on the existing state-of-the-art algorithm, what is the pointing accuracy of our method? Question 3. What is the difference in user experience between our method and traditional method? We first designed a three-stage pipeline to implement the occlusion-based object selection system on the mobile phone, object detection, and target prediction. We opened the front and rear camera to take pictures simultaneously. We first used the linear pipe iris to locate the 3D position of the user's iris, which uses the RGB image from the phone's front camera with a depth error of less than 10%. And then, according to the known and fixed geometry relationship between the front and rear cameras, we can obtain the occlusion area and the user's perspective in the rear camera images. Secondly, we performed the object detection algorithm YOLO version 4 to locate the bounding box of all interactable objects, and then we had to estimate the probability of each candidate object. We first conducted a user study to collect data and analyze the user's target selecting behavior with phone occlusion. We recruited 11 participants from our institution and built a virtual room scale scenario containing 49 everyday objects in VR. The users must stand in a specific position to select the 49 objects in the room 3 times. Users are informed about the concept of occlusion-based object selection and are asked to complete actions quickly and naturally. By collecting user behavior data, we found 4 important features. 1. Users tend to believe that the invisible area corresponding to the intersection area of the two occlusion rectangles formed by the left and right eyes. 2. Users believe that the most accurate position was align the phone's center with the targets. 3. Users tend to rotate the phone to match the object's main axis, holding the phone horizontally for fat and wide objects and holding the phone vertically for thin and tall objects. 4. Users deemed that putting the phone closer or further to their eyes to select larger or smaller targets made sense. Considering the above factors, we chose the distance-weighted Jaccard index to establish our target predicting algorithm. We approximate the occlusion and target rectangles as 2 bivariate Gaussian distributions and then compute the similarity of shapes using the above equation. In study 2, We evaluated the pointing area of our method and prototype system. We recruited 20 participants from our institution and conducted this experiment in a real room. We hung a crosshair target on the wall and asked the user to aim the corner of the phone at the target and take photos. Each user needs to use the left or right eye to aim at the target through the phone's 4 corners 5 times and different eye target distance and eye-hand distance settings. According to the analysis, we find that the main factor causing the estimation error is the inaccuracy of the iris depth estimation, which corresponds to the radially outward distribution in the figure. Our method achieved an average corner error of occluded area estimation of 1.28 degrees, acquired with a general model without calibration toward users. The average pointing error was further reduced to 0.65 degrees if we calibrate for each participant. We conducted a third user study to evaluate our prototype system's efficiency, accuracy, and usability. We chose the first 3 existing camera-based object selection techniques from previous work as our baseline for comparison. In addition to the 3 existing baseline methods, we proposed 2 methods to extend the concept of using the phone as a real-world physical cursor. Except for the first baseline of opening the camera to take pictures, the other methods do not require rendering the camera preview. The 6 candidate method all use the center-to-center distance as the similarity measure. We recruited 13 participants from the local institution and conducted this study indoors, where we prepared 31 electrical devices as interactable candidates. When the user raises the phone and taps the screen, the phone will speak the name of the select device via voice feedback and display its name on the screen. We measured the time and accuracy. After participants had fully experienced each techniques, we interviewed them to collect their subjective feedback. We asked them to fill out the NASA TLX questionnaire and the system usability scale as a metric to evaluate user experience. The results showed that our method is comparison in accuracy to photographs and faster than existing baseline methods. Users consider it convenient and efficient. From users' feedback, we found 2 key points. The first is providing effective visual feedback so the user can confidently select the target. The second is that when there is no camera preview, it is easier to occlude the target from the user's perspective instead of pointing at the target with the phone's camera or head gaze, which show the potential for user perspective interactions. Thank you for your attention. For more details, please refer to our paper.